गैस एसी ऑन करना
नहीं है क्या?
नहीं है सर। अब सेट कर लीजिए सर, टेम्परेचर थोड़ा हाई है अभी 28 पे रखा हूँ मैं।
कम कर दूंगा, ठंड लग रही है।
सर
ठंड लगती है।
नहीं मतलब अभी ठीक होगा सर, अब देख लो।
Now, after this pattern and the different shrinkages and different types of pattern, core print, and then chaplet, chills, all we discussed. And now we'll discuss, a very important topic in that casting, gating system. That is design of your gating system. So basically that gating system is nothing but the passage through which this molten metal is to be poured in your mold cavity in order to get a defect-free casting. Now, the first thing is, why do we use this gating system? We can directly pour that molten metal into the cavity, isn't it? We have the cavity, we can directly pour this molten metal by using that ladle. Okay. Why do we need this gating system? Right. The first question is, see, if we have the mold cavity and if we are directly pouring that molten cavity without using this gating system, what will happen? You will get some defect in your casting. For example, suppose if say if you have to make an aluminum cube, okay, by using that casting process, and if you are directly pouring that aluminum molten metal into the cavity, so what will happen? There will be oxidation, right? There will be oxidation of that aluminium and it will form the aluminium oxide. So it will form the aluminium oxide, and this oxide is nothing but it's a kind of defect in your casting. So avoid the different defects that we can have without the gating system. We'll use the passage. Obviously there are number of elements of this gating system, we'll discuss about it, so that we will get the casting which will be free from the defects. Okay, so to avoid the defect we use this gating system through which this molten metal is to be poured in your casting cavity. Now, what should be the different requirements? What should be the different requirements of your gating system? So you can see this slide on your screen. The first thing is, in order to get the defect-free casting, there are some requirements that your gating system should have. So the first thing is, the pouring time should be as minimum as possible. That is, the first requirement is pouring time should be as minimum as possible. Why this pouring time should be as minimum as possible? Because say this is your So this is your, say, getting system. Okay. So this is your getting system through which this molten metal is to be poured in your cavity. So the pouring time should be as minimum as possible, because if the pouring time is very high, so what happens in that case, your molten metal will solidify somewhere in the passage. Say here it has been solidified. So it has been solidified means obviously your cavity will not get completely filled. Okay, so in order to avoid that, this pouring time should be minimum. Pouring time should be minimum so that your cavity gets completely filled. Your molten metal should not solidify in the passage. So obviously once it has solidified somewhere in the passage, your cavity is not get completely filled. So you will have defect. So that defect is known as Misran defect. We'll discuss that. What are the different defects that we have? So the first requirement, pouring time should be as minimum as possible. Second is no turbulence. There should be no turbulence in your getting system. No turbulence. No turbulence of your molten metal in the getting system. Okay. In order to avoid that sand erosion and all that. And the third is impurities should not enter in the mold cavity. So there are number of impurities that is present in your molten metal. Okay. So obviously your getting system should able to separate the different impurities that is present in your getting system. Then only you will get the casting which will be free from the defects. So it will have some element which should be able to filter that impurities. Okay, like filter it should have. So obviously there are a number of things that we have in the getting system. That generally what it does is it separates the impurities that is present in your getting system. Okay. So the third thing is impurities should be separated. Okay. Impurities should be separated. Impurities should be separated from your molten metal. Next thing is no aspiration effect. No aspiration effect. The fourth point is no aspiration effect. What exactly that aspiration is? Say this is your passage. So this is your complete mold. Say this is your complete mold. Now this is your getting system. We'll discuss the different elements that we have. We have this. So basically this is, say it is filled with that molten metal here. So here we have. So here we have. So basically this is your pouring basin. This part is called the sprue, and this is your runner, and here at this, the point at which the molten metal enters is called the ingate or gate, and then somewhere in between that your runner we have the skim bob. Okay, so this is your skim bob, and here we have this splash core. This part is called. Okay. So these are the splash core, or we can say this is sprue base wheel, or I can write This is your sprue base well, this part. Now, so this pouring basin and sprue runner ingate, and then some important like skim bob, then sprue base well. These are the important element of your gating system. So the fourth point, that the fourth requirement of your gating system is no aspiration effect. What does that mean? No aspiration effect means your pressure inside this gating system should not fall below the atmospheric pressure. Why? Because if the pressure inside your gating system is below that atmospheric pressure, the air from the outside will start flowing inside your gating system. So the air from the outside will start flowing into that gating system. Why? Because of the porosity of your molding sand, porosity, or I can say permeability of your molding sand. Okay, so if the pressure inside your gating system falls below that atmospheric pressure, the air from the outside, so obviously there will be some pressure difference inside your gating system and outside your that mold, and the air from the outside will start flowing into that gating system. So once there is a air inside your gating system, this air present with that molten metal will cause that blowholes in your casting. Okay, so that is why inside the gating system, your P inside that gating system should be greater than P atmospheric pressure. So pressure inside your gating system should not fall below that atmospheric pressure in order to avoid that aspiration effect, in order to avoid the air present in your gating system. And why it is happening? Because of the permeability or porosity of that molding sand. Okay, permeability is the property of that molding sand is the ability of that molding sand to escape the air or gases that is present in your molten metal or inside that cavity. Okay, so because of this permeability, this air from the outside will start flowing into the gating system if the pressure inside your gating system is below the atmospheric pressure. So there should not be any aspiration effect. The first thing, pouring time should be minimum in order to avoid the solidification of that molten metal in your gating system, to avoid the defect. Second is no turbulence. There should not be turbulence of that molten metal. Third is it should have the ability that it should able to separate the impurities that is present in your molten metal, and no aspiration effect. Pressure inside your gating system should not fall below the atmospheric pressure. Then proper thermal gradient. There should be proper thermal gradient. This again is the requirement of your gating system. Fifth one, proper thermal gradient. Proper thermal gradient. Okay, there should be proper thermal gradient in order to have the progressive solidification of your molten metal inside that gating system. Means obviously the molten metal should solidify here in the mold cavity, then it should solidify in that passage. If the molten metal solidify inside your gating system, obviously it will restrict the flow of molten metal into the cavity. So that is why there should be proper thermal gradient, that is your temperature difference with that time, that is dt upon that dt time. And then there should not be any mold erosion. Then sixth requirement is no mold erosion. There should not be. So obviously the velocity of that molten metal inside the gating system should not be very high. Why? Because if the velocity of that molten metal inside that gating system is very high, it will cause the erosion of your sand inside that gating system. So there should not be any erosion of that sand, because once the sand is eroded, what will happen? Obviously that during solidification your casting will contain the sand. Again your casting will be will have some defect because of that sand in which is mixed with that molten metal. So there should not be any sand erosion. Okay. So these are the different requirements of your gating system. These are the different requirements of your gating system. That is your gating system should have in order to have the casting free from defect. Okay. So these are the requirements, and now we'll discuss what are the different elements that we have. Different elements of your gating system. Okay. So that I have written here. It's a pouring basin, the first one, a sprue. Then we have this sprue base well. Then we have runner. We have skim bob, and we have ingate or gate. And all the elements have different functions. Different functions are in the gating system. We'll discuss. So different elements of your gating system. Now we'll jot down the elements of gating system. The first element that we have is pouring basin. We have the pouring basin. The second element we have is sprue. The third element is sprue base well. The next we have runner. Fifth element we have runner extension. Then we have ingates. Or gate. Ingate or gate, and seventh is the riser. So these are the different elements that we have in your gating system. So this is the first element that we have, pouring basin. It's nothing but reservoir of molten metal. The second element we have sprue. Third element is sprue base well. Fourth element we have runner. Fifth element is the gate, and say the sixth element that we have, a riser that is placed on the top of your mold cavity. So here it's a blind riser. Okay, blind riser up to some depth from your mold cavity. Now we'll discuss each element one by one. Okay, the first we will discuss the pouring basin. What exactly that pouring basin is. So what exactly that pouring basin is? So pouring basin is nothing but it's a reservoir of that molten metal. Okay. So this pouring basin is nothing but the reservoir of molten metal. So basically the main function of the pouring basin is to reduce the momentum of that molten metal. Okay, reduce the molten of that momentum of that molten metal. So that is why here you can see some inclination is given to that surface of your pouring basin. So here we'll pour the molten metal on the surface. So it will reduce the momentum of your molten metal. And this pouring basin will also, what will do is, it will separate the impurities. The first thing is a reservoir of molten metal. It reduces the momentum of that molten metal. It also separates the impurities that is present in your molten metal. Here you can see that. Okay, here you can see that. Here we have a skim bob. This is your skim core. So the high density impurities will be collected at the base, and here we have the lighter impurities. Lighter impurities will be collected on the top. So this pouring basin is a reservoir of molten metal. The main function of this pouring basin is to reduce the momentum of that molten metal. it also separates the impurities that is present in the molten metal. So high density impurities will be collected at the base, and lighter impurities will be on the top. Okay, and obviously there should be full flow. There should be full flow through this full flow of that molten metal through this pouring basin, so that it will avoid entering the air into your mold cavity. So there should be full flow through this pouring basin. And here you can see this is your strainer core. This is your strainer core. So this the metallic plate coated with this ceramic, having the number of holes, so that again it also acts as it also separates the impurities that is present in your molten metal. At the same time, it will maintain the constant head in your pouring basin. Okay, so this is the main function of your pouring basin. It's a reservoir of molten metal. It reduces the momentum of that molten metal. It also separates the impurities that is present in the molten metal. There should be full flow through this pouring basin in order to avoid the air entering into that mold cavity. And also we have this strainer core in order to separate the impurities and also to maintain the constant head in the pouring basin. So this is basically what that pouring basin is. Now then we have this sprue. A sprue is nothing but it's a connecting passage between your pouring basin and the runner. Okay, so it's a connecting passage. It's a connecting passage between pouring basin and runner. So it's a connecting passage between your pouring basin and the runner. Pouring basin, you can write down some points. It's a reservoir of molten metal. The first point. Second point, you can write down. It also separates impurities and reduces the momentum of molten metal. There should be full flow. There should be full flow, through this pouring basin. Okay. And this sprue is a connecting passage between your pouring basin and the runner. It's a connecting basin. And here you can see we have used a sprue which is tapered. We are not using the cylindrical sprue. The reason of using this tapered sprue is to avoid that aspiration effect. Aspiration effect means pressure inside your getting system should not fall below the atmospheric pressure. Okay, so that is why we have considered, the shape of the sprue is tapered in place of that cylindrical sprue. We'll see that how, we'll try to prove that this shape of the sprue should be tapered, cylindrical tapered. So pouring basin we discussed. Sprue is a connecting passage between your pouring basin and a runner, and we use that tapered shape. So you can see the slide on your screen. Some important points regarding that pouring basin and sprue. So the first point that we have is pouring basin is a reservoir from which this molten metal enters smoothly into the sprue. We have to make the constant head. Okay, it reduces the momentum, the main function of that pouring basin. It separates the lighter and heavier impurities by using that skim core. Okay, the next thing is it reduces the momentum of that molten metal so that it enters into the sprue without any turbulence. The main function of that pouring basin is to reduce that momentum of that molten metal. The next thing is a strainer core. A strainer core that you can see here. It's a ceramic coated screen with that number of holes. Okay, is used to maintain the constant head in the pouring basin, to maintain the constant flow of that molten metal. The next slide that we have about regarding that sprue is a connecting passage between the pouring basin and the runner that I have written here. The next thing is a straight tapered circular cross section. So the shape of your sprue should be tapered. It's a straight tapered whose cross section should be circular. Okay, is used in order to avoid the aspiration effect. Aspiration effect means to maintain the pressure inside your getting system greater than the atmospheric pressure. And height of the sprue is responsible for producing the required velocity of the molten metal in the getting system. And it is the height of the sprue which will give you the required velocity at which this molten metal will enter into your mold cavity. We'll discuss, we'll try to find out how that velocity of that molten metal depends on the height of this sprue. We'll discuss that. Then the next slide is about a sprue base well. You can see on your screen a sprue base well. It is used. It's a reservoir of molten metal at the bottom of your sprue to reduce the momentum of that molten metal, to avoid that sand, the sand which will go with that molten metal into your mold cavity. Okay, it is used to avoid that sand erosion at the base. The next point, that it reduces the mold erosion. The main purpose of using this sprue base well. Okay, then we have this runner. Then again, you can note down some important points regarding this runner. Runner is a connecting passage between this sprue and then ingot. Ingot is the last point in your getting system at which this molten metal enters into your mold cavity. So runner is a connecting passage between your sprue and ingot. The next point that we have, it is horizontal with the uniform trapezoidal cross section. Obviously the cross section of your runner should be trapezoidal. It's a uniform trapezoidal in cross section. Okay, so horizontal with uniform trapezoidal cross section. Why trapezoidal shape of this runner is used? Because this shape, this uniform, that trapezoidal shape have the maximum that CD, coefficient of discharge. Okay, that is why we use this trapezoidal cross section. Then the mainly used for minimizing that sand erosion. This runner is used to avoid the sand erosion. The main purpose of using this runner. And the next that we have is the runner extension. Okay, runner extension that you can see in your slide that is given on, that is shown on your screen. That runner extension is some extension that is given to that runner in order to collect that that impurities that is coming from your molten metal. So initially when we pour this molten metal through the ladle into that pouring basin, so what will happen? Your molten metal will contain some of this slag. Okay, initially when we start pouring. So when we pour that molten metal, it flow through that pouring basin, then into a sprue, then runner, and it goes into that runner extension. So basically runner extension is used to collect that slag from that molten metal. Okay, so it will collect, and then this molten metal will enter into the ingot, okay, or gate. So this runner extension is again used to collect that slag that is present in that first molten metal. First molten metal means initially at this time of starting of the pouring. Okay, it will separate the slag that is present in your molten metal. That is what we use this runner extension. Then the last element that we have is gate or in-gate. So it's the last point of your gating system through which this molten metal enters into your mold cavity. Okay, it's the opening through which this molten metal enters into your mold cavity. Now, what about its shape and cross section? Obviously, again, the shape and the cross section should be such that it can be easily broken off after the casting solidification. It can be easily broken off means, say, once we have poured this molten metal into the cavity, so some of the molten metal will be in your gating system also. So with that molten metal in your casting cavity, with that molten metal in that gating system, so is solidified. So what happens is, like, we'll have to trim that. We'll have to trim the molten metal that has been solidified in your gating system and riser also. Okay, in order to get the the required the casting. So its shape should be such that it can be easily trimmed. It can be easily machinable. Okay, so that we can remove that part which has solidified in your gating system. Okay. Again, its shape should be same as that of the runner. Its cross section should be trapezoidal. Okay. And it can be easily trimmed out after casting solidification, and it allows the molten metal to enter quietly into your mold cavity. Okay, that is the main purpose of your gate or in-gate. So either we can use one gate, you can use the number of gates. Now, how will you classify that gating system? That you can see on your screen. Classification of that gating system. So we have the top gating system, we have bottom gating system, and we have the side gating system. There are a number of the advantages of these three these gating system. We'll discuss that. So we discussed the gating system is required in order to have the defect free casting. We saw some of the requirement that your gating system should have in order to avoid the different defects that we can have. Okay, pouring time should be minimum, no aspiration effect, impurities should be separated. Okay, there should be no any sand erosion. And then we discussed about the different elements, pouring basin, reservoir of molten metal. Okay, it reduces the momentum of that molten metal, and then it also separates the impurities. There should be full flow in order to avoid the the air from entering into that gating system. And we use that strainer core. It's a metallic plate coated with that ceramics with the number of holes. So to maintain the constant head, at the same time the molten metal can enter smoothly into your sprue. Sprue is a connecting passage between your pouring basin and your runner. Okay, it's a straight tapered with that circular cross section in order to avoid that aspiration effect. Then a sprue base well to avoid the sand erosion at the base of your sprue, because the height of the sprue is responsible for the required velocity. So at the sprue base will have the maximum velocity of that molten metal. So if we do not have the sprue base well, so obviously this molten metal with very high velocity will cause the sand erosion at that sprue base. So there we have that sprue base well in order to avoid the sand erosion. Then we saw the runner. It's a connecting passage between your sprue and the in-gate. Okay, so obviously it is used to avoid the sand erosion, and its shape should be uniform. It's a horizontal uniform trapezoidal in cross section. Then the runner extension, we saw that. Okay, so runner extension, some extension in that runner is given in order to separate the slag that is present in the first molten metal at the time of start of the pouring the molten metal from that ladder. Okay, so it will separate the slag. Then we saw the in-gate or gate. Okay, is the last point in that your gating system is the opening through which this molten metal enters into your mold cavity. Okay, cavity, and its shape should be same that it can be easily trimmed off, because the molten metal in the mold cavity and also some of the molten metal in the gating system will also be solidified. So the molten metal which has been solidified in your gating system should be trimmed. should be trimmed, should be machined in order to remove that. Okay, so it can, its shape is again, you know, the trapezoidal, its cross section is trapezoidal. Why trapezoidal? Because it has the maximum coefficient of discharge. Then the classification, as I said, that there are three types of gating system that you can see on your screen: top gating system, bottom gating system, and side gating system. So there are a number of advantages and disadvantages of this gating system. We'll discuss one by one. Okay, and we'll start with that top gating system. We'll start with the top gating system. You can see the important points regarding that top gating system on your screen. The first point is that in the top gating system, molten metal enters the cavity from the top with atmospheric pressure at the base. Now see, in top gating system, so gating system will discuss its classification. We discuss, as I said, there are three types of gating system: top, side, top, bottom, and side. We'll start with that top gating system. Top gating system. And in top gating system, the molten metal enters in the cavity from the top with atmospheric pressure at the base. At the base, means say this is your pouring basin, this is your pouring basin, and this is your sprue. Okay, this is your sprue, and this is your mold cavity. So this is your mold cavity. So this is your pouring basin, pouring basin. This is your sprue. Okay, and this is your mold cavity. Mold cavity. So in this, the molten metal enters the cavity from the top. So that is what that top gating system means. The molten metal enters into the cavity from the top. Now the second point is favorable temperature gradient towards the gate is achieved. What does that mean, favorable temperature gradient? Favorable temperature gradient means initially when that molten metal start that filling that cavity, so initially the molten metal will be collected at the here at the base. So the molten metal in that mold cavity will start solidifying from the bottom of the cavity towards the top. Okay, so initially the molten metal will solidify here, then here, then here, here. So this is the progressive solidification. So progressive solidification. So suppose if we have the riser which is placed at the top of your cavity, so obviously the molten metal once is start solidifying from the bottom, so the riser will be able to fit that extra molten metal to avoid that shrinkages. It's not like that this molten metal will start solidifying at the top. So once it is solidify at the top, so obviously the molten metal from this gating system will not be able to fill that cavity, because the molten metal which is solidified on the top will restrict the flow of that molten metal. So in this top gating system, the molten metal will start solidifying from the bottom of the cavity towards the top. Okay, so that is we are getting the favorable temperature gradient from the bottom towards the top. Okay, so we will have the casting which will be free from the defect. So it is written in this slide, you can see, it means metal from the gate will reaches to the bottom of the cavity, obviously, initially, and hot molten metal will be present at the top. So hot molten metal present at the top, so obviously it will take more time to solidify than the, obviously, the molten metal which is collected at the base. Okay, so the molten metal will start solidifying from the bottom towards the top. So there is no any, the restriction that is given by that molten metal which has solidified. then the advantage is design is simple and can be used for a small casting. But the thing is design is simple. You can see here there is no runner is used, and can be used for a small casting. If we use this top gating system for a casting which are very deep, the cavity which is very deep, in that case what will happen? It will cause the sand erosion. Sand erosion at the base of your mold cavity, isn't it? Because as I said that velocity is directly proportional to that height, okay? So obviously the velocity at base will be very high, it will cause the mold erosion. Okay, so this top gating system is used for that small casting. The small casting means the casting which are not that much deep. Okay, so for the casting which are very deep, we will not use this top gating system. For a casting whose height is very high, so in that case it will cause the sand erosion at the base. So again you will have the casting which will have some defect. Then the next point is disadvantages are like turbulence and erosion, because the metal fall directly into the cavity through a height. Obviously, as I said, that disadvantages we cannot use for a casting which are very deep. For large casting we cannot use that, and can be used where the mold are erosion resistant. Okay, so if say mold cavity whose surface is coated with some material, if we have made that surface that erosion resistant by coating that surface with some materials, so in that case there is no problem with that pouring that molten metal with that top gating system, because we have already coated the surface, and the molten metal which is entering at very high velocity into the cavity will not cause any erosion. Okay, and higher casting yield. What does that higher casting yield means? Higher casting yield means say in this we can see casting yield. I can write casting yield. So in top gating system we are getting the higher casting yield. Casting yield means weight of the casting upon the total weight of your molten metal. Means what I am trying to say is weight of your casting plus the weight of the molten metal which has been solidified in your gating system and your riser. So the total weight of your molten metal. So in this top gating system we are not using any runner and all that. So obviously we will not have the molten metal, extra molten metal that will solidify in your runner. Okay. So obviously it will give you the higher casting yield. So casting yield is the weight of casting upon weight of casting, or weight of the casting plus weight of molten metal solidified in gating system and riser. That is your total weight of your molten metal. That is what it means. So here we are not using any runner and all that. So you will have this the lower value, the denominator will be less. So the casting yield will be very high in that case. So higher casting yield we will get in the top gating system. Now we'll discuss, how will we, as I said, like we do not use that straight, the cylindrical shape of this probe. In place of that, we use the straight tapered with that circular cross section of this probe in order to avoid that aspiration effect. We will try to do that. And then we'll try to find out the time taken by the top gating system to fill that cavity. that is your pouring time. What I said is we do not use that straight cylindrical sprue. In place of that we use the straight tapered. Okay. So say the cross section at this is your say 2 and this is your cross section 3. Okay, so cross section at the entry of your sprue is A2 and cross section at the exit of your sprue is A3. So this is your A3 is cross section at exit of sprue and A2 is the cross section at the entry of sprue. What we are trying to do is we are trying to find out the shape of your sprue. Okay, we are trying to find out the shape. What should be the shape? Here we have, what I have done is I have drawn the taper. So we don't know. Now we don't know the shape of your sprue. We are trying to find out what should be its shape, or what should be its shape in order to avoid the aspiration effect. Okay. So A2 at the entry of the sprue, A3 is the at the exit of the sprue. Now we know the flow behavior of that molten metal in this gating system is given by the Bernoulli's equation. Okay, Bernoulli's equation, and we can also use that equation of that continuity. Okay, so by using that equation of continuity, I can write A2 V2, okay, equal to A3 V3, where V2 is the velocity of the molten metal at the entry of the sprue and V3 is the velocity of the molten metal at the exit of the sprue. Because obviously this pouring basin will have some height, say it is HT from your datum we have taken as the exit of the sprue, and H2 is the height of your sprue. Okay, so we'll use that Bernoulli's equation and continuity equation in order to find out what should be the actual shape of your sprue. So the molten metal is flowing through this gating system here. So by that equation of continuity we can write down that A2, that is the discharge at 2, will be equal to the discharge at 3. That is the cross section 2 is equal to discharge at 3. Now A3 upon A2 equal to that V2 upon V3, and what I do is, like we consider or we make some what we do, we take that ratio of that area at the sprue base upon that area at the entry of the sprue is R. So we assume that R equal to say A3 by A2. Okay. Now just apply the Bernoulli's equation at the section 2 and 3. Now at the section 2 and 3 we'll apply that. So P2 upon rho plus V2 square upon 2 plus G H2 equal to P3 upon rho plus V3 upon 2 plus 0. So at section 2 and section 3. So by using the equation of continuity, I can write A2 V2 equal to A3 V3 at section 2 and 3. Now what I am doing is applying the Bernoulli equation at 2 and cross section 3. So P2 upon rho plus V2 square upon 2 plus G H2, where H2 is the height of the as proof from your datum. Datum we have taken as the base of your S proof. Now, to avoid the aspiration effect, the pressure inside your getting system should be greater than the atmospheric pressure. It should not be below. Okay, it should not be below the atmospheric pressure. So, what we assume is the pressure inside your getting system is atmospheric pressure. Minimum pressure inside your getting system should be equal to the atmospheric pressure. Then only what will happen, there will not be any aspiration effect. So what we assume is inside your at P2 and P3, that is your P2 which is equal to P3 equal to P atmospheric pressure. This is the assumption that we are making. The pressure at 2 and 3 is equal to the atmospheric pressure, because this is the condition to avoid the aspiration effect. Pressure inside your getting system should not be below the atmospheric pressure. It can be greater than atmospheric, but it cannot be below. Okay, so we are assuming that P2 and P3 equal to atmospheric pressure. Okay, so once it is P2 and P3 is P atmospheric, so that P2 and P3, which is your gauge pressure, will be 0. Now, because we have the pressure gauge which give you the gauge pressure, okay, which give you the gauge pressure. So gauge pressure means greater than the atmospheric pressure. Okay, so obviously this P2 and P3 will be 0. 0. We are considering that at section 2 and 3 pressure is atmospheric pressure. Okay, atmospheric pressure. So atmospheric pressure means P2 and P3 is your gauge pressure. So P2 and P3 will be 0, because the pressure gauge that we use to measure the pressure gives us the gauge pressure, not the absolute pressure. Okay, so gauge pressure means the pressure above that atmospheric pressure. We are measuring the pressure by keeping that datum at the atmospheric pressure. So P minus the P atmospheric, so that P2 and P3 will be 0. Okay, so V2 square, this V2 square upon 2 plus that GH2 equal to V3 square upon 2. So this is the equation that we are getting. Okay. Now we have this R, this is equal to the R, V2 by V3 equal to that R V3. Sorry, V2 by V3 equal to R. Okay, now just put the value of V2 in terms of that V3 here. So this is your, say, equation number 1 and this is your equation number 2. Okay, so put the value of that V2 in terms of that V3 and R. So I can write V2 square will be R square into V3 square, R square into V3 square upon 2 minus, I can write V3 square upon 2, which is equal to minus GH2. Okay, I can write this. So, or I can write R square minus 1, which is equal to minus 2GH2 upon V3 square. Or I can write R equal to or directly I can write R equal to square root of 1 minus 2g h2 upon v3 square. Okay, I can write R equal to square root of this 2g h2 upon v3 square. And v3 square is nothing but 2g ht. So square 1 minus 2g h2 upon 2g ht. So 2g will get cancelled. So you will get 1 minus h2 upon ht, which is equal to that R. R is nothing but the ratio of the area. It means the shape of your sprue should be, because this is the shape, this is the equation that we got the ratio of A3 upon A2, and it tells us that its shape should be parabolic. Okay, so tells us the shape of your sprue should be parabolic. Parabolic. So the actual shape should be parabolic. Here, your sprue shape in actual should be parabolic. But it's very difficult to make that parabolic shape. Manufacturing is somehow difficult. It's very difficult to manufacture that. So what we do is, by keeping the cross section of 2 and 3 is as same as that of your parabolic sprue, we make that parabolic shape into a straight tapered. Okay, by keeping the same cross section at 2 and 3, we make that parabolic into a straight tapered, so that pressure at any point in your getting system will be greater than, obviously, that the shape that is given by that parabolic shape. So we are keeping the same cross section at 2 and 3, and we make that parabolic into a straight tapered, so that pressure will be obviously greater than atmospheric. We have done this derivation by keeping the pressure at 2 and 3, which is equal to that atmospheric pressure. So if we are making the cross section area at any section in your sprue is greater than the cross section area given by that parabolic shape. So we are making the cross section area greater than the parabolic shape. So means we are, obviously, the pressure at any point will be greater than the atmospheric pressure. Okay. So we are increasing the area. Okay. So you can see, you can just in case of, say, nozzle. Okay, nozzle is like increasing the velocity at the expense of pressure, and in case of nozzle, its area is continuously decreasing. Okay, area is continuously decreasing, velocity is increasing. So at the exit, that nozzle has the smallest that cross sectional area. So at that point, the velocity will be maximum, and obviously pressure will be minimum. Okay, the same concept. So to ease that manufacturing, we are making the straight tapered in place of that parabolic shape. Okay, so that is why we have taken that straight tapered sprue in our diagram, in order to avoid that aspiration effect. And this is the condition to avoid that aspiration effect. R equal to square root of 1 minus h2 by h2. R is nothing but the ratio of the cross sectional area. Cross sectional area means area at the exit upon that area of the area at the entry of your sprue. Okay. So by increasing the area, we are increasing that pressure. Now the next thing is, how will you find out that pouring time? Pouring time means the time taken to fill the cavity by using the top gating system. Here we are talking about the top gating system. How will you find out the time taken by the top gating system to fill that, to completely fill that cavity? Okay, so now we'll discuss the pouring time in top gating system. So this was all about, the shape. How do we, check the shape of your screw? So the shape, the ideal shape should be the parabolic, but its manufacturing is difficult. So what we do is, we keep the cross section at the entry of the screw and at the exit. We keep that cross section as same as that of the parabolic shape, and then in between that we make that cross section into that straight tapered, so that pressure at any point will be greater than the atmospheric pressure. Now we'll discuss how to find out the pouring time. Pouring time is nothing but the time taken to fill that cavity, to completely fill that cavity by using that in top gating system. So this is your top gating system. Here you can see that this is your top gating system, and this is your this is your sprue, and here we have this is your sprue. So say here we have this molten metal in your pouring basin and in a sprue, and it will completely fill your cavity, fill your mold cavity. This one. Now H2, this H2 is the height of your sprue, and HT is the height of your pouring basin, height of the molten metal in the pouring basin. So H2 is your height of sprue, and HT is your height of molten metal in pouring basin. Now how do you find out the pouring time? Okay, this, say I denote this pouring time by, say, PT. Okay, PT or TP, something like that. So how will you find out that pouring time? Now before how to find out that pouring time, we'll find out what is the velocity of the molten metal at the exit of your sprue. We'll try to find out the velocity of the molten metal at the entry of the sprue, and obviously here it will have the velocity will be 0. So this is your section 1, this is 2, and at the exit we have the section 3. Okay, so A2 is the cross-sectional area at entry of sprue. A3 is cross-sectional area at exit of sprue, and say V2 is the velocity of molten metal at entry of sprue, and V3 is the velocity of molten metal at exit of sprue. Okay. Now to find out the velocity at the exit of the sprue, we'll apply that Bernoulli's equation. So what I can write is we'll apply the Bernoulli equation at section 1 and section 3. Okay. So we'll get the velocity at 3. Obviously the total energy at the section 1 and 3 will remain constant. So P1 upon rho plus V1 square upon 2 plus G HT equal to that P3 upon rho plus V3 square upon 2 plus 0. And obviously this P1 will be 0, pressure at the entry, and P3 should be 0 in order to avoid that aspiration effect. Okay, and obviously velocity here at 1 because we have to make the constant head, so V1 equal to 0. Okay, so velocity at the section 1 will be 0. So you will get V3 equal to that a square root of 2G HT. So velocity at section 3 or at the exit of your sprue is nothing but the square root of that 2G HT, where HT is here the height of your molten metal in the pouring basin from your datum that we have considered at the base of your sprue. Okay. Now, suppose we don't know this height HT. And we have only we know is that height of the sprue, and suppose we know the velocity at that at the entry of the sprue is say V2. Okay, we don't know the height of the pouring basin, just we have the velocity at the entry of the sprue, and it is given that S2 is the height of the sprue. Now they will tell you to find out the velocity at the exit of the sprue. How will you find out? Just apply that Bernoulli equation at the section 2 and section 3. Simple. By keeping that pressure equal to that atmospheric pressure in order to avoid that aspiration effect. So if you will apply that Bernoulli equation at section 2 and 3, you will get V3 equal to square root of V2 square plus 2G H2. So this velocity is in terms of if you know the velocity at the entry of the sprue and height of the sprue. This is for if you know the height of the molten metal in the pouring basin. Okay. So in this way we can find out, by applying that Bernoulli equation, we can find out the velocity. We can find out the velocity at different locations in your getting system. Okay. Now once we know the velocity, our next job is to find out the pouring time. Time taken by the getting system to fill that cavity. Yes. So time taken is simple. It's the time taken to fill the cavity by using that top getting system is given by this time taken, or pouring time is given by the volume of casting. Okay, or directly I can write volume upon that discharge. So where V is the volume of the casting and Q is your discharge. So I can write now V upon area. Area may be area at area minimum into V maximum, or volume of the casting upon A max into V min. So we have already discussed how to find out the velocity at the section 3. Velocity at section 3 is nothing but the velocity at the exit of the sprue, and it is the point where the cross-sectional area is the smallest, right? We are getting the minimum, that cross-sectional area at the exit of your sprue. So once we know that cross-sectional area at 3, and once you know that velocity, and if you know that volume of the casting that we have to make, we can easily find out the pouring time. So pouring time is nothing but the volume of the casting upon discharge. Okay, so discharge, if it is given, discharge is given, directly put the value, that is volume upon that discharge, you will get that pouring time. Or in GATE what they do is they will give you the cross-sectional area at the exit of the sprue, and they will give you the height of the pouring basin or height of the sprue. If we know that velocity at the entry of the sprue, we can find out the velocity at the exit. We know the cross-sectional area, we can find out discharge. Once we know the discharge and volume of the casting, we can find out the pouring time in the top grading system.
हूँ सर।
6 बजे।
हम थोड़ा बाहर से कह रहे तो प्रिंट कर रहे हैं।
अच्छा कितने बजे? अच्छा हाँ 6 बजे जाऊँगा। ठीक है। Now we have a bottom gating system. Okay, so in bottom gating system, the molten metal flow into that mold or mold cavity through the bottom of the mold cavity. So in the top gating system, we saw that molten metal enters into the cavity from the top. Here in bottom gating system, the molten metal enters from the bottom of the cavity. Okay, and so what are the different advantages that we will have by entering that molten metal from the top of the bottom of the cavity? Obviously, there will not be any turbulence, and obviously the erosion of that molding sand will be minimum. What I mean to say is, here we have this pouring basin. Here we have this pouring basin. Here we have this pouring basin. Okay. So here the molten metals enters from the bottom of your cavity. So by pouring that or by entering that molten metal from the bottom, obviously there will be very less erosion. Erosion will be minimum, and metal at the top of the cavity will be at lower temperature. Metal at the top of the cavity will be at lower temperature. That means there will be unfavorable, temperature gradient. In top gating system, we saw that there was a favorable temperature gradient. Means the molten metal will start solidifying from the bottom of the cavity towards the top. Okay, so that what will happen means the riser will be able to provide that extra molten metal. Okay, but in case of bottom gating system, the case is different. Means the molten metal will start, that is the hot molten metal will be present at the bottom. So suppose in bottom gating system, if you are having the riser at the top, okay, so obviously what will happen is this riser will not be able to feed that extra molten metal into the cavity during that shrinkages. Okay, so this is the one of the problem that we have with this bottom gating system. Okay, bottom gating system. But the advantages is like erosion will be very less. Okay, will be very minimum, and this bottom gating system is mainly used for that deep molds that you can see in the slides that are on your screen. And obviously, as compared to that top gating system, it takes the higher time to fill the mold. That is pouring time, I can say. Pouring time to fill the cavity in bottom gating system is greater than the top gating system. It is generally 2 times. If the mold height is equal to the HT. So this is say this is your datum. So this will be your HT, and this is your height of the S blue, and this is your HM, height of your mold. Okay, and preferable with the use of side riser. As I said, in bottom gating system we are not getting the favorable temperature gradient. So if we keep the riser on the top of the cavity, so this riser will not be able to feed that extra molten metal because the hot metal is present at the base. So the molten metal which is solidified somewhere near the top will restrict the flow of molten metal. So the shrinkages that is taking place at the bottom will not be compensated by this riser. So that is why in case of that bottom getting system, it is preferable to use the side riser. Okay, it is preferable to use the side riser. Side riser say something here we can say. Side riser. Okay, the riser placed in the side of your mold cavity. Then only it will be able to fit the extra molten metal, even the molten metal has solidified in the top. Okay, so that is why this bottom getting system is preferable with that side riser, and obviously that it is used for the deep mold. Okay, so these are the points that you can see. It is on your skin. Now in this we will discuss how to find out the pouring time. Pouring time, that is the time taken to fill the cavity in case of that bottom getting system. So here we have, suppose this is your pouring basin here, and say the height of the molten metal in the mold cavity at any instant, say it is h. Okay, this is your section 1. At the base we have section 2, here we have 3, and here we have 4. So now apply the Bernoulli equation at 1 and 3. Apply that. So 1 and 3. So P1 upon rho plus V1 square upon 2 plus GHT equal to P3 upon rho plus V3 square upon 2 plus 0. Okay. So P1 pressure at 1 is atmospheric, so we'll take 0. V1 will be 0. So GHT equal to that P3 upon rho plus V3 upon 2. Now after filling that cavity up to height h, velocity at 4 is very small, and what we can do, we can consider that velocity, it tends to 0, so we take it 0, and after filling that cavity up to height h, this molten metal has lost its momentum, and we consider that again V3 is so we will find out the pressure at 3. What we have made the assumption is like after filling the cavity up to height h, velocity at 4 is very small, and we neglect it. Okay, so V4 is 0. Now we have to find out the pressure at 3. Okay, so apply the Bernoulli equation at section 3 and section 4. So once you apply it, you will get P3, that is P3 equal to rho G H. Okay, you will get that. Okay, pressure at 3 equal to rho G H, because velocity at 4 is very small. Okay, and we have neglected that. So P3 equal to rho G H. So rho G H, now just put that P3 into this equation. So GHT equal to rho GH upon rho plus V3 square upon 2. So this will be rho will get cancelled. So V3 equal to square root of 2G H T minus H. This is the velocity with which this molten metal is entering into your cavity. Okay, in case of that bottom getting system. Now this is the velocity with which it is entering into the cavity. Now what we will do is what we will do is the height of that molten metal in the mold cavity has increased from H, has increased by say dH. Okay. Now what we have considered is the height of the molten metal in the mold cavity has increased by height dH. Okay. So the height has increased by dH, so the volume of the molten metal in the mold cavity has increased by the area, that is this area, this cross-sectional area of your mold. This is, say its area is say Ag. Okay, so what we have assumed is the height of the molten metal in this mold cavity has increased by height dH. So once this height is increased by dH, so volume will be increased by Ag times dH. So this volume of the molten metal in the mold cavity has increased by Ag into dH. Now this volume of the molten metal in the mold cavity, okay, this volume should be same as that of the volume of the molten metal that has entered through the section 3. It should be same. Okay, the volume will be remain same, because then only the height of the molten metal in the mold cavity will increase by that dH. Okay, so this volume should be same as that of the volume of the molten metal entered through the section 3. Then only height of the molten metal will increase in the mold cavity, or the volume of the molten metal will increase in the mold cavity. So I can write this Ag into dH equal to A3, okay, A3 into V3 into dt. I can write that. So this is the volume of the molten metal entering through the section 3 should be equal to the volume of the molten metal that has increased in your mold cavity. Okay, so Ag into dH equal to A3 V3. So I can write Ag upon A3 into dH upon V3 is square root of 2g ht minus this one. So square root of 2g into ht minus h, which is equal to dt. Now we have to to fill the cavity, obviously the height should be hm. Means say it takes time t to fill the cavity of height hm. So we'll integrate that. We'll integrate it from 0 to t. T is the time taken to fill the cavity by using this bottom getting system. Now t is the time taken to fill the mold cavity of height hm. So of height 0 to hm. Okay. So if you will do the integration, you will get the expression that will give you the time taken by the bottom getting system to fill the cavity. And that will be this pouring time so time will be am by ag, some am by ag, okay. Or we'll integrate that, okay. we'll integrate that. What we'll do is dt, integration of dt will be t, which is equal to ag by a3. So ag by a3 into 1 by root over 2g. Okay, and integration of say 0 to hm dh upon say square root of ht minus h. Okay, so we take that x equal to say ht minus h, so dx will be minus dh. Okay, so when h equal to 0, so when h equal to 0, x equal to your ht, and when h equal to hm, your x equal to ht minus hm. So I can write ag upon a3 into 1 by root over 2g, integration, it will be ht to ht minus hm, it will be minus dx upon the square root of x. Okay. The square root of x. Now do the integration of that. Minus dx upon this one. So ag upon a3 minus, say we'll take that, into 1 by root over 2g, and it will be x to the power minus 1 by 2 plus 1, so x to the power 1 by 2 is square root of x, and 1 by 2, so it will be 2. Okay, so it will be into 2 into the square root of ht minus square root of ht minus hm. So this will be your pouring time. So this is the pouring time in case of the bottom gating system. So in this way you can find out the pouring time in the bottom gating system, in the top gating system, and the velocity at different, the different section in the SPRO. So this is very, very important, because in gate is actually, it's a completely numerical. So from casting, either you will get the question from that shrinkages means they will ask you to find out the volume and side after that shrinkages, and or they will tell you to find out the velocity at the exit of the sprue at any section. They will give you the height of the sprue or height of the molten metal in the pouring basin, or they will tell you to find out the pouring time in top gating system and in bottom gating system. So these are the formula and the derivation which you can apply to find out the pouring time and velocity in your gating system. Now after bottom gating system we have the side gating system. Now you can see this slide on your screen. In top gating system, what we studied is like the molten metal enters into the cavity from the top. In bottom gating system, we studied that molten metal enters into the cavity from the bottom. Okay, bottom of your cavity, and the time taken in bottom gating system is greater than the top gating system. Okay, but in case of top gating system, the casting yield is high. Casting yield is high means obviously there is less scrap, I can say, because that casting yield is nothing but weight of that casting upon the weight of the casting plus the molten metal solidify in your riser and your in gating system. But the advantages with the bottom gating system is like mold erosion is less. We can use this for the casting which are deep, that we cannot use, in that case we cannot use the top gating system. But in top gating system, what we saw that there was a favorable temperature gradient. Favorable temperature gradient means molten metal started solidifying from the bottom of your cavity. Okay, so even if we are having the top riser, there was not that much difficulty in fitting that extra molten metal in your cavity. Okay, but in case of bottom gating system, what we saw is that there was an unfavorable temperature gradient, means the hot molten metal was at the bottom. So if we are using the riser, so in that case the riser will not be able to supply that extra molten metal in order to compensate that shrinkages. Okay, so that problem with that bottom gating system is avoided by using the side gating system. So in side gating system, what we do is molten metal enters into the mold cavity from the side. Either we can have the one gate or we can have the number of gates, okay, on the side of your cavity. So that what will happen in that case, if you are keeping that gate or in gate at the parting plane, okay, at the parting plane, so what will happen means half of the cavity will be filled by that bottom gating system and half of the cavity will be by the top gating system. Okay, so in that case again we are avoiding the unfavorable temperature gradient. Okay, unfavorable temperature gradient. So that unfavorable means it started solidifying, say, from the top. So the riser will not be able to fit because the molten metal has already solidified in the top. Okay, so it will restrict the flow of that molten metal. Okay, so it solves the next point that we have, it solves the problem raised in the bottom gate, that is unfavorable temperature gradient. That is why we use this side gating system, and it is used for large and heavy casting. Obviously it's used for large and heavy casting, because in that case in bottom gating system can be used for large casting or deep casting. Okay, but the problem is that unfavorable temperature gradient. Okay, so wherever we have the large and heavy casting, we'll use the side gating system, and it is very easy to make that that gating system on the parting plate, or that runner and that in gate at the parting plate. It's easy. Okay. Then the next gating system that we have is parting gating system. It's a side gating system. By keeping that means we can say the molten metal enters into the cavity through this parting plane, at the parting plane. So metal enters the mold at the parting plane by keeping that runner and in gate at the parting plane, likely to cause mold erosion if the drag portion of the mold cavity is deep. As I said, if you are keeping that that in gate at the parting plane, so half of the mold cavity will be filled by bottom gating and half will be filled by top. So your drag part will be filled by the top gating system. Half will be filled by, just like here we have this say gate, and here we have. So this half will be filled by top gating system and this will be filled by bottom gating system. So if that drag portion is deep, this one, if that drag portion is deep, it will cause the mold erosion again. But it is easier and most economical in preparation. So that is why mostly we use that parting gating system. Then the next question that we have from engineering services, which was asked in 2011, and you can see this question on your screen. We have to measure that. It's like measure the following. On the left side we have top gate, bottom gate, parting gate and step gate. On the right side we have heavy and large casting, then most widely used and economical. Third option we have is like turbulence, and the last one is unfavorable temperature gradient. So in top gating system, we saw that mold erosion and turbulence. So we'll match that top gate with that turbulence. Bottom gate, unfavorable temperature gradient. So option 4. Then parting gate is most widely used and economical. So option 2, and step gate. It is used for that large and heavy casting. Now the next we have is this classification of the gating system. we saw like how that molten metal enters into the cavity. Based on that, how molten metal enters into the cavity, that we have discussed. Now we will discuss the type of the gating system based on that pressure. So basically we are having the two type of gating system: pressurized gating system and unpressurized gating system, that you can see in this slide, which is on your screen. So the first one is the pressurized gating system, right? So in pressurized gating system, what happens? There are some points in that. The first point we have is the total cross-sectional area decreases towards the mold cavity. Total cross-sectional area decreases towards the mold cavity. That means we are talking about the cross-sectional area at the base of the screw. We are talking about the cross-sectional area of the runner. Because in runner we discussed is runner is a horizontal passage which are uniform in cross-section, and it's trapezoidal. That the cross-section is trapezoidal. So total cross-sectional area decreases towards the mold cavity means we are talking about the cross-sectional area at the base of the screw. We are talking about the cross-sectional area of the runner, and then we are talking about the cross-sectional area of the ingate. So basically what we are trying to say, so based on the pressure we have pressurized gating system, and then we have the unpressurized gating system. Unpressurized gating system. Now in pressurized gating system, the total cross-sectional area decreases towards the mold cavity, means we are talking about the AS, AR and AG. Where AS is the cross-sectional area, this is your cross-sectional area at the base of your sprue. AR is the cross-sectional area of runner, and AG is the cross-sectional area of ingate. We are talking about this three area. Okay, so this cross-sectional area decreases towards the mold cavity. It means this AG will have the smallest cross-sectional area among these three. So this is what that pressurized gating system is. So once this cross-sectional area decreases towards the mold cavity, it means wherever we are having the smallest cross-sectional area, at that point we will have the minimum pressure. Just apply that same concept as we discussed in case of that nozzle. Because the smallest cross-section area we are having at the exit of the nozzle. At that point we are having the maximum velocity and again minimum pressure. So pressure will be minimum at the here AG, and at that point pressure will be maximum. Because the smallest cross-section area is at the ingate. So at that point we will have the minimum pressure, right? And we will have the maximum pressure at the base of your sprue. It means obviously we are talking about the back pressure. Okay. So back pressure is maintained. Back pressure from that back. Okay, back in your gating system is maintained. Now when there is a back pressure, so there will be full flow. When there is a back, means someone trying to push you from the back. Okay, so obviously there will be full flow through your gating system. Your gating system will be completely filled by that molten metal. There is no, any gap, okay, and there will not be any void in your getting system. There will be complete, the flow, completely full flow through your getting system, because there is a back pressure in your getting system. It's not like that AG is minimum, so you are getting the minimum pressure, so it should be named as the, that the unpressurized getting system. No, pressurized getting system means we are talking about the back pressure, okay, pressure that is trying to push that molten metal, that is trying to maintain the full flow in your getting system. Once there is a back pressure in your gate system, that is your getting system, what will happen? There will be full flow, there will not be any void. There will not be any void means there will not be any aspiration effect. That is what written in the point. So back pressure is maintained, flow of liquid is almost equal from all the gates. When there is a back pressure, so obviously if you are having the number of in gate, okay, number of in gate, so obviously from all the in gate there will be, the flow of liquid will be equal from all the gates. Now back pressure helps in reducing the aspiration. Obviously it will reduce because there is a back pressure, so there is no void, so obviously there will be no aspiration effect. No void means obviously the air from the outside will not enter into your getting system. Okay, so there is no air, no aspiration. No aspiration means no that defect in your casting. Then high velocity leads to more turbulence and chances of mold erosion. But the problem with is, like here we are having the minimum area at the gate, we are having the minimum pressure, but at that point we will have the maximum velocity of the molten metal. It means the molten metal is entering into the mold cavity at maximum velocity. So when there is a Vmax at the maximum velocity with which the molten metal is entering into the cavity, it means it will cause the erosion. It will cause the erosion and turbulence. Okay, so in case of pressurized getting system, we will have the turbulence and erosion, but at the same time there is a back pressure which will try to avoid the aspiration effect. Simple. Now, in case of unpressurized getting system, unpressurized getting system is, in case of pressurized getting system, the cross-sectional area decreases towards the mold cavity. So it will be opposite of that pressurized getting system. Here, this AS, AR, and then AG. Cross-sectional area will increases towards the mold cavity, means towards that gate. So here at AG will be max. So cross-sectional area at that gate is maximum. It means velocity will be minimum and pressure will be maximum, because area is maximum. So area is maximum, pressure maximum, but velocity minimum. When there is a maximum pressure at the in gate, obviously back pressure, there is no back pressure. Okay, so here the back pressure is not maintained. Back pressure is not maintained. When there is no back pressure, means there will be aspiration effect. Okay, so once there is an aspiration effect, air will enter into your mold cavity and you will have the defect in your casting. But in the unpressurized getting system, we are getting the minimum velocity with which that molten metal is entering into your cavity. So minimum velocity means there will not be any erosion. Okay. So the point that is written here is like total cross-sectional area increases towards the mold cavity. Back pressure is not maintained, as I said. So not maintained means aspiration effect. Flow of liquid is different from all the gates. There is no back pressure, so flow of that molten metal through all the gates will not be uniform. And since velocity is minimum, so less turbulence and less chances of that mold erosion. Okay. So these are the important points that we have about that pressurized and unpressurized getting system. In unpressurized getting system, this getting ratio is generally 1:4 that you will have to remember, and in pressurized it is 1:2:1. So pressurized 1:2:1. That you will have to remember. Sometimes in some exam they will directly ask you what is the ratio. This ratio of that cross-sectional area is known as the getting ratio. getting ratio. So getting ratio is the ratio of that cross-sectional area of the sprue at the base, and then cross-sectional area of the runner, and then this in-gate or gate. So casting yield, as I said now, casting yield is actual casting weight upon the weight of molten metal entered into the mold. This is. So we have discussed about what actually that casting process is, and the first thing in casting was to make the pattern. So we made that pattern. By using that pattern, we made that mold cavity. Okay, we made that mold cavity. Once we have the mold, we poured that molten metal by using this getting system, and we discuss in getting system we discuss what are the different requirements, and then what are the different elements that we have, why do we use this getting system, what are the different classification of that getting system is, what are the different advantages and disadvantages. Then we discussed about how to find out the velocity at different section in your getting system, and how to find out the pouring time, okay, in the top getting system and bottom getting system we discussed. Okay, the next thing is to find out the solidification time. Okay, solidification time is like how much time once it is molten metal is poured into the mold cavity, how much time it takes to solidify. We have to find out the time taken by that molten metal into the mold cavity to solidify. And it was given by that Chevorinov's rule that solidification, that heat present in your molten metal is directly proportional to that volume. Okay, and the transfer of heat or cooling rate is directly proportional to that surface area. So solidification time is by Chevorinov's rule, I can write that solidification time is directly proportional to that square of the volume, and inversely proportional to the square of the cross section, that surface area. Okay, so we'll discuss about the solidification time. We'll discuss about the solidification time. Okay, so solidification time by Chevorinov's rule, what he said is like the solidification time is directly proportional to the square of the volume, and it is inversely proportional to that square of that surface area. It is not the surface area of that casting. Okay, we cannot say that. It is AS, V is the volume of casting, and AS is the area I can write surface area through which that that is heat is dissipating, I can say. Okay, so AS is the surface area which is exposed to heat transfer, is the surface area exposed to heat transfer. So suppose if we have to make a, say, cube, we have to make a cube by using that casting process. So this V is the volume of that cube, volume of your casting, and AS is the surface area which is exposed to heat transfer. So in some case what happened, the top surface may be insulated. Top surface may be insulated means there is no heat transfer through this top surface. So V will be, say, suppose this is a cube of side A, so its volume will be A cube, and its surface area will be, surface area which is exposed to heat transfer will be 5A square. So this is not the total surface area of the casting. It is the surface area which is exposed to heat transfer, the area through which the heat dissipation is taking place. Okay. So by using this formula you can find out the solidification time, and we'll solve some the question from this solidification time, how to find out that. We'll solve some question from that solidification time and also from that getting system. Now, this question is from GATE 2017, set 1. And the question is, it's like, you can write down as proof, this is GATE 2017 and set 1. The question is, a sprue in a sand mold, a sprue in sand mold has a top diameter of 20 mm, has top diameter of say 20 mm and height 200 mm and height 200 mm. The velocity of the molten metal at the entry of this sprue, velocity of molten metal at entry of a sprue is 0.5 meter per second, and assume G equal to 9.81. Assume G equal to 9.8 meter per second square, and then neglect all the losses. All the losses means that friction and all that losses we have neglected, because in derivation we have neglected all the losses. in that Bernoulli equation. All the losses, and if the mold is well ventilated, the velocity of molten metal at the bottom of this sprue. So we have to find out the velocity of molten metal at the exit of sprue is at the exit of the sprue is. We have to find out. So it is given as a sprue instant mold has a top diameter of 200 mm. So this is your sprue. So here we have diameter equal to 20 mm. Okay. So this is your section 2 and this is your 3. And height is 200. So height of the sprue is 200 mm. Velocity of the molten metal at the entry of the sprue is here. So here V2 equal to 0.5 meter per second. Assume G equal to 9.8 meter per second square, the velocity of molten metal at the exit. So we have to find out the velocity at 3. Okay, so we have already discussed that V3 is equal to square root of V2 square plus 2GH2. If we know the velocity at the entry of the sprue, so it will be square root of 0.5 square plus 2 into 9.8 into 0.2. So you will get 2.043 meter per second. So this will be the answer for this question. Now the next question we have from mechanical engineering in 2005. So this is your GATE 2005 ME, and the question is a mold has a down sprue whose length is 20 centimeter. So a mold which has a down sprue whose length is say 20 centimeter, its length is given, and cross-sectional area at the base of the down sprue is 1 centimeter square. Here A3 equal to 1 centimeter square. Now the down sprue feeds a horizontal runner leading into that mold cavity of volume 1000 centimeter cube. So mold cavity, so volume is 1000 centimeter cube. So the time required to fill the mold cavity will be. So we have to find out the pouring time. So pouring time we know volume upon the discharge cube. So volume is 1000. So 1000 upon cube discharge. Discharge is area into velocity. So area is 1 into velocity will be 2 into 981 into 20. Okay. So this will give you 5.05 second. This will give you 5.05 second. Okay. Now the next question that we have was asked in GATE 2007 ME. Okay, and it was for 2 marks. The question is a 200 mm long down sprue has a cross section area of 650 mm square. Okay, where the pouring basin meets the down sprue. So we have the down sprue. Okay. its length is 200 mm, so its length is 200 mm, and so a 200 mm long down sprue has an area of cross section of 650 mm square, where the pouring basin meets the down sprue. So at this point, pouring basin meets the down sprue. So at this point, cross section area is 650 mm square. So this is your section 2. So A2 equal to that 650 mm square. Now, a constant head of molten metal is maintained by the pouring basin. The molten metal flow rate is 6.5 into 10 to the power 5, means Q equal to 6.5 into 10 to the power 5 mm³ per second. Discharge is given. Okay, considering the end of the down sprue to be open to the atmosphere, this is open to the atmosphere, and an acceleration due to gravity G equal to 10 to the power 4 mm per second square, I think. Okay, so the area of the down sprue in mm square at its end, avoiding the aspiration effect. So we have to find out the A3. Okay, we have to find out the A3. So now what will we do is, like, A2 is given, we know the discharge, so obviously we can find out the V2. So we know that Q equal to A2, V2 equal to A3, V3. Okay. Now Q equal to itna, so Q equal to 6.5 into 10 to the power 5 equal to A2 is A2, V2, which is A2 is 650 into V2. Okay. So we can find out V2. We'll get some, and it will be mm per second. So you will get V2. Now once we know V2, we can find out the V3. Now what will be the V3? V3 equal to square root of V2 square plus 2G H2. H2, this is your H2. So this V2 will be your 1000, right? So V3 equal to square root of this V2 is your 1000 square plus 2 into G is 10 to the power 4 into H2. Okay, and it is 200. So from here you can find out the V3. Okay, some value you will get. It is in mm per second. Now Q equal to A3 V3, so I can write Q equal to A3 V3. So Q equal to 6.5 into 10 to the power 5 upon V3 will give you the A3. Okay, and this V3 you will get it from here. So A3 will be something 290.7 mm square. So this will be the answer. 290.7 should be the cross-sectional area at the base of the sprue in order to avoid the aspiration effect.